This video shows how the user data rate can be improved in different propagation environments. If beam pattern of 5G base station is optimized according to a large difference of angular spread of radio wave energy in the space. The angular spread of radio wave is similar to the spread of light by fog and in vertical direction is much smaller as compared to horizontal direction in the most of propagation environments. Hence, the antenna pattern can be matched according to these differences. The story begins when the character, called Peter, starts to download a file while leaving home on his way to work. Before reaching the office, Peter walks through 6 different propagation scenarios and experiences higher data rate due to 5G base station antenna array shaped optimization. The first propagation scenario is millimeter wave 28 GHz 5G small cell deployed in suburban environment. In this case, a line-of-sight path between 5G base station and Peter's smartphone occurs, and reflections of radio waves from different objects still cause spread of radiated energy in the space. Hence, optimization of antenna array shape from 8x8 to 16x4 improves effective antenna gain by 1 dB and allows to increase the downlink data rate by 75 megabits per second in 400 MHz channel bandwidth. The second scenario still assumes millimeter wave small cell deployment in suburban area. However, in these cases a non-line-of-sight condition occurs, which leads to more significant spread of radiated energy due to larger propagation scattering, and thus benefits more from antenna pattern optimization. Optimized antenna array improves the effective gain by around 3 dB, which allows to increase a downlink data rate even by 180 megabits per second. The third presented propagation scenario illustrates sub-6 GHz, 3.5 GHz, urban macro 5G cell deployed in open square area, which enforces line-of-sight visibility. In this case, the angular spread of radiated energy is negligible, and optimization of antenna pattern does not generate noticeable improvement. The fourth scenario, on the other hand, allows to get additional 40 megabits per second of downlink data rate in 100 MHz channel bandwidth, due to optimization of antenna array shape from 12x8 to 32x3 when deployed in urban macro 5G cell. Optimization was feasible because even in line-of-sight condition, the spread of energy occurs, and effective antenna gain is improved by almost 2 dB. In the fifth scenario, which is millimeter wave small cell deployed in urban micro street canyon environment, an improvement of 340 megabits per second in downlink data rate is obtained. Such a significant difference results from more than 2 dB higher effective antenna gain due to optimization of antenna array shape from 16x16 to 64x4, 800 MHz of available channel bandwidth and line-of-sight channel condition. In the last scenario, where a non-line-of-sight condition is assumed for urban micro deployment, the large spread of radiated energy through the street canyon environment allows for significant improvement in effective antenna gain, which is almost 6 dB. Such an increase in effective antenna gain allows improvement of the downlink data rate by 270 megabits per second, again in 800 MHz channel bandwidth.